Hello everyone and welcome to this new video. Um, I'm Alban Tuet and I'm going to present today a small video about how to interpret a black box in machine learning. So this video will explain to you some advice about how to use interpretability, generally speaking. It will be divided into two parts. The first one will be um, small explanation of what is interpretability and what's the main uses of interpretability and AI. And the second part will be a use case about spam detection algorithm, and we'll try to interpret how this algorithm is working. Okay, so before we start, I'll just check whether the live is on. Yeah, it seems like it's working. So this presentation, sorry, will last for approximately 1 hour, probably a little bit less. I will try to read your comments if you have any, but as you can see, I'm alone, so it's going to be difficult for me to manage both the live and the questions. So I won't answer any of the question as soon as you ask them, but I'll try to check regularly if there are any. Also, this presentation will be recorded, so uh, if you want to see it again, or if you are seeing if you are seeing it already on YouTube, you will always be able to see it again on our YouTube channel. Okay, let's start. So, the question of interpretability in modern machine learning is pretty recent. Of course, machine learning is a new domain, so it's hard to say that it has any of the question about machine learning can be old. But the question of how to make sure that the model is working as we want it to do is pretty new. The thing is that uh, uh, 20 days ago, it was very easy to understand how algorithms were working because they were fully coded by the informaticians. The people that were creating the algorithms were controlling everything that was made by the machine, or most of what the machine was doing. And if the machine was doing something that was not uh, uh, made it to do, the informaticians would have to correct it, and it will not scare people. Nowadays, if you ask the question to your neighbors or to your friends, you will probably see that a lot of people are actually scared about what intelligence, artificial, and more generally speaking, algorithm can do, especially because we are aware of the fact that we don't understand everything inside those algorithms. The thing is, the machine learning and the artificial intelligence domain has considerably rise during the last decade, and nowadays it's uh, very easy to create an algorithm that is so complex that you won't have enough of your entire life to understand it fully. So the question we want to ask today is, how can you be sure that your model is doing what you want it to do, even if you don't understand everything that's happening inside it? It's not an easy question. There are many ways to do. We'll try to give you an overview of the different techniques that you can use and that you can implement in your everyday lives. Okay, so first of all, let's talk about a concept that is used a lot in artificial intelligence, which is the concept of a black box. Usually, a black box is something that we cannot look inside. It's something that is made so that you won't be able to understand what's happening inside, because you cannot access to it. In machine learning or in artificial intelligence, a black box is a little bit different because you could look inside. You are able to open the black box and try to look at what's inside it, but it's so complex that you won't be able to understand it even if you wanted to. So what's happening is that you will usually have some inputs like a video, an image, some text, or I don't know, some information, personal information about people. The algorithm, so that we will call black box here, will make some transformation. It will maybe make some operations with the data you gave it. Maybe he will create random figures also. He will use very complex neural network algorithm, and then it will create an output, which is the prediction of the model. So let's say you want to create a model that is able to predict the weight of someone based on his age, his nationality, and his size. You will be able to have something here that makes a lot of operations in order to calculate the the weight of this person. Um, the the main principle here to understand about interpretability is that you will have to look at both the inputs and the outputs to understand what's going inside the black box. You most of the time won't look directly inside the black box because it's too hard. It takes too much time, and it's easier just to look at what's the relation between the input and the output. The objective you want to get is to be able to, in some ways, predict what's going to be the results of your model when you use it on a specific input. For example, you want to be able to say that if you try your model, if you execute your model in on a specific sample of someone that is has a specific size, a specific age, and a specific nationality, you want to be able to say, okay, for this particular sample, the model will predict this value or around this value. But what it is for? Why do you want to be able to predict the way the model is working? There are many reasons why you would like it to be that way. The first one is that in order to convince maybe your boss or to convince the legislators or your clients, you want to be able to show to them that your model is working as they are expecting it to work. So, for example, if you take the Tesla car that is automated, uh, the Tesla car needed to be able to prove that even when it's working on a real street with real people in front of it, it won't have a strange behavior. So how did the Tesla engineers worked in order to do so, to convince people? They created an interpretability model. So they try to explain their black box, which were the cars or the algorithm used in their cars. And this interpretability model was able to show how the car was working, especially how the algorithm that was given the camera, the video of the car was working. And if you try to look at it on the internet, you would be able to see that the algorithm based on the video camera of the Tesla, is detecting every single people and every single element of the street, like the roads, the lights, the people, the other cars, etc., etc. And they are showing bounding box, so like little squares around those objects, in order to not to work better, but to show to the rest of the world that it's working as we expect it to work. So it's showing that it really detects people, it really detects objects, it really detects other cars, just like a human do, and this is what we want him to do. Also, in some specific cases, you will need to show that your model meet legislative requirements. Let's take an example of a company that is building an algorithm in order to be able to classify the curriculum vitae, to say whether it's a good or a bad curriculum vitae. Very simple. We would like to make sure that the model is not using information that they shouldn't use, like, for example, the sex or the nationality or the age of the person we would like to classify. And so interpretability model will make you able to make sure that the model is not using those forbidden information. Uh, the, the third reason why we would like to use interpretability models is to detect potential biases. So let's say you have a model that is working very well on the data you had in hand. You cannot be sure that this is going to work on the real data, on the real inside the real world, because most of the time the data you're giving to your model to train itself are very different to the data you're going to give the model in order to make some real prediction. The data you will have in your laboratory when you're training the model will most of the time be very uh, well labelized. They will be well organized. There won't be so much errors, and also it will be a little bit older than the real data, so it will have probably a lot of biases. Let's take a concrete example. In data scientist training, we one time created a project in order to detect COVID, so the disease, on uh, um, lung radiography. So we had a database of lots of lungs radios. Some of them were some of them had COVID, some of them not, and we wanted to have a classification model that was able to say whether this radio, the patient who had this radio was given the COVID or not. And the problem we faced is that very quickly our model was able to classify very well those radiography. So we were a little bit doubtful, and we used interpretability method to see where the model was looking at. And we saw that the model didn't look at the lungs like we expected it to do, but he looked at everything that was outside the lungs, like the small artifacts that were present on the radiography. And those artifacts didn't say anything about the COVID in itself, but it said a lot about the machine and the hospital where the radio was made. And when we looked at it closer, we saw that most of the radio that were classified as COVID were coming from the same hospital, and even worse, from the same machine and the same doctor. So all those radio was at pretty much the same aspect, with the same artifacts, the same tools, etc., etc. And the model was very strong to detect those artifacts, and not strong at all to detect COVID. So detecting potential biases is probably one of the most useful way uh, to the main reason why we want to use interpretability methods. The fourth one is to help with decision. So this is going to be very pretty quick. If you have a model that is able to detect cancer, for example, a lung cancer, you don't want him just to say, okay, this person, this patient has cancer and this doesn't have, because it's very hard to trust 100% the model, and you don't want to risk people's life in this decision. So what you would like the model to do is to say, okay, this person has probably a cancer because I saw that there were a lesion here in this radio, for example. And so the interpretability method will give you not only the way the model is working, but also the direction in where the model is looking at. So for example, I detected a cancer because of this specific bunch of pixels that is a little bit darker than what it should be. And so this will help the radiologist, for example, to finally make the final decision, and which will not be only based on the model. For almost the same reasons, you will be able to improve the performances of your model in some situation, not all the time, based on those feedbacks. For example, if you see that your model is not looking at the right direction, he's looking at the top of the lungs while he should look at the middle of the lung, you can maybe try to pre-process a little bit better your data, because you know that if he looks at the middle of the lung, it will have better performances. Finally, you could also use these interpretability methods to understand better the problem. So let's say you have a model, again, that is able to classify people to say whether they have cancer or not. Let's suppose that this model is having better results than even the best radiologist in the world. You could try to see how the model is working, to try to understand why this is working better than the radiologist. Maybe because it's not only looking, I don't know, at the lesions in the lung, but also the shape of the lungs or the size of the lungs, and some things that weren't taken into account before, and that you will be able to use in order to understand the problem better and to improve the way the classification is made. Okay, so as you can see, there are lots of reasons why we want to use interpretability, um, even if the reasons don't apply in every single sector. I believe that in every single project where there is artificial intelligence implied, there is a reason why we should use interpretability. So now that we know what is interpretability and what's the reason why we need interpretability, let's look at what's concretely interpretability. So there are two main uh, um, way of using interpretability. There are two main models of interpretability. The first one is called global interpretability. The second one, local interpretability. For global interpretability, the objective is to explain the general behavior and the tendencies of the model. So let's say you have your model that is able to make the classification between cancer and not cancer. Uh, the global interpretability will tell you that, generally speaking, your model looks at the shape of the lung or the size of the lung in general. For local interpretability, it will explain the prediction of the model at the level of an individual, a sample, a patient. So it will tell you that for this specific patient, not in general, the model looked at the shape of the lung, or it looked at the top of the lung. So of course, this requires a greater precision because you need to do it for every single individual or every single sample, so it has a greater a smaller effect on the model. um, but this is in a lot of cases what you want to have. So for example, let's have another example, another use case. If you as a bank are using a model in order to predict whether this is a good idea or not to give a loan to somebody, if the model tells you, okay, no, this is not a good idea to give a loan to this specific person, you would like to be able to tell the person the reason why you weren't able to give them a loan, and not only because the model said so. Probably you can tell it that you would be able to give him a loan if he came back in a few years because it's too young, or maybe you will be able to give him a loan if he has a little bigger a salary a little bit bigger, or maybe if he's married, I don't know. So those features can be reached with local interpretability. But if you only have a global interpretability method, you will just be able to say, okay, generally speaking, if you are a little bit richer, you will be able to have a loan, but I'm not sure that in your specific situation this will work. Okay, so we saw that there were two main domains in interpretability, but there are also two ways of talking of interpretability. There are two main way of working. The first one is what we call specific interpretability, and I personally think that this is not this is not really interpretability when you think about it. What I told you before with this slide is that when you are trying to look inside the black box, you can not understand anything because it's too complex. And so what you're going to do is that you won't look inside the black box, but you will only look at the relation between the input and the output. However, in some specific cases that you may know, for example, when you're using linear regression, the black box is not very black. It's very easy to understand what's going inside. And so you will be able to use specific interpretability, so a model that is specific to linear regression, to understand what's going on inside this black box. So even if I think that it's not interpretability, properly speaking, this is probably the easiest way and the better way to work when you are using something that is not as complex as a deep neural network, for example. So when you have a linear regression, logistic regression, random forest, you should use specific interpretability to make sure that you have a strong comprehension of what's going inside the model. So what this means is that you will specifically look at the parameters that were calculated inside the black box and maybe compare them, maybe add them together, try to use some operation to give some feedbacks about how the model is working. And for specific interpretability, you can have both global and local interpretability depending on the model you are using. So specific interpretability, of course, is reserved for less complex model. You won't be able to use it for very complex model. And the thing that is very interesting is that there is no approximation necessary. We will talk a little bit about it later, but as you can see, understanding the relation between the input and the output is very vague. Like there is not only one way to do it. There are lots of ways to look at it as it is, and usually we say that the interpretability methods will be approximations of what's going inside the black box. It's like we will approximate how the input and the output are working together. But for specific interpretability, this is not how it works. Sorry. There is not any approximation used, and so this is exactly how the model works. Um, so if you want to use specific interpretability, you would be able to use it with, for example, decision tree, random forest, linear regression, logistic regression, also with XGBoost. And to do so, I will try to show it. Okay. You will be able to do it using some methods, some attributes based on the scikit-learn library. So for example, here, you can see that there is an attribute called coef, and this attribute will give you the estimated coefficients for the linear regression problem. If there are multiple targets, and if there is one day of length and features, yeah. So this will give you a way of understanding what are the coefficients that were learned in order to make the linear regression. So for example, if you have two inputs like x1 and x2, and one output is y, linear regression will try to predict y with a linear combination of x1 and x2. So uh, you will have two coefficients predicted, let's say a and b, so that you will try to optimize a and b so that a times x1 plus b times x2 will be close to y. We can understand that a and b will give you all the information to need in order to understand how the model is working. And for example, we can say that if a is a lot bigger than b, then probably x1 is a lot more important than x2. So there are some approximation about what I'm saying here, but this is what you should remember of the specific interpretability of the linear regression. I'll try to see if there are any questions before I continue. Yeah, this is sorry, took comments. Okay. Hello to everyone who said hello. Let's continue. Feel free to ask a question if you had anytime. I won't answer right away, but I'll do my best. Share screen. Okay. So now that we know how specific interpretability works, we'll talk about the big deal, which is agnostic interpretability. So as I said earlier, what we would like to do is to understand what's inside the black box by looking at the relation between the inputs and the outputs. So the agnostic method will use the model. It will try to simulate the model by giving some inputs and looking at the outputs. There are many ways to use the agnostic methods, but you need to keep in mind that this agnostic method is a model in itself. It's like you use a model on top of a model. This is why in some cases you will see the term middle model for the fact that you used a model to understand better another model. Um, the main reason why we will use agnostic interpretability is because we can use it to a whole category of models. So any model that use inputs and outputs can be used with agnostic method. However, contrary to specific interpretability, is based on approximations, because you won't be able to get everything that is coming inside the black box. Maybe there are some phenomena that you won't be able to see because you won't give the right inputs and you won't look at the right outputs. Let's take a concrete example. If you look at the correlation between the inputs and the outputs, so let's say we take the example of the model that is trying to predict the weight of someone based on his age, his size, and his nationality. we will try to look at the correlation between age, nationality, size with the weight. And it's probably that we will see that the nationality is not related to, so it's not correlated with the weight, but the size is a lot correlated to the weight. So we will probably see some kind of correlation, and if the model is using those information correctly, we will be able to see that the inputs like the size and the output, the weight, will be a lot correlated. Okay. So this is a very, very simple agnostic method. There are others that are more complex that we will talk about it, but you see the idea here. We only need some inputs and some outputs. We don't need anything else. Okay, so now that you see what is an interpretability model and that you see the difference between specific and agnostic, we will try to get along some uh, main groups of agnostic interpretability methods. So the first one we'll talk about is the approximations. So because we have very complex models here, we would like to have something simpler here that will be able to do almost the same job. So for example, let's say we have transformers with convolutional neural networks and time series, etc., etc. We would like to be able to do something that is similar to the black box, but with a model that we will be able to interpret using specific interpretability. To do so, we will have many ways to do. The first one is to say, okay, I will just use like a linear regression or a random forest to, in some ways, simulate the black box. But of course, it seems a little bit weird because the reason why we used a black box is because we weren't able to make the right prediction with a simpler model like a random forest. However, the agnostic method, you need to remember, is not based on the same data set. It doesn't use the real label, it only uses the output of the black box. Moreover, let's say that your model needs lots of data, but you don't have enough. So the black box is based on a small amount of data. Your agnostic method will be able to have as many data as they want because they are not limited in that way. The reason why is they can give some random inputs or to make even some inputs and look at what's outside. So even if they are not real patients, so let's say you invent data about someone that is 10 years old and French and that is 1 meter and 48 centimeters. Even if this data is not existing anywhere in the world, you will be able to look at the output of the model and you will be able to use those in a couple of input and output to create the agnostic method, to be able to use this agnostic method. So this is great because it means that you won't have any limit in terms of data. You will be able to use your agnostic method and to train it with as many data as you want. But as you can see with the example I took, if you just create random inputs and you look at the output of the model, you may have to look at some points in your space that don't exist and that won't ever exist. Like for example, a 10 years old guy who's with a size of 2 meters. This doesn't exist. There is not any people in the world with this specific information. So what you will face is that this model, this agnostic model, will be based on some inputs that are not relevant, some information that are not relevant. So even if, let's say you say, okay, I can see that my model is giving a lot of importance to, I don't know, the nationality, which shouldn't be something that it is important in that model. uh, Maybe it's because you looked at some specific spaces in your data set that are not relevant, and your model so made irrelevant predictions about those data points. So even if the agnostic method will give you a strong and a very a good approximation of how your model works, generally speaking, it won't give you a good approximation of how the model works in the space that you are looking at, that is that you want to give attention to. So for example, the 10-year-old people that have a size of 1 meter and 30 centimeters. Okay, so the problem you will have here is that there is for the agnostic method, if you create new input, you have no idea if those inputs are relevant or not. So you have to be careful about that. And so for this reason, the global approximation method that we would like to use, so to say, okay, we would like to do exactly the same thing as the black box, but with a simpler model. So for example, like a random forest, you will be able to do it. Your random forest model will work, but the importances of the features of the random forest here are not the same as the one in the black box, or at least are not the same in the right space. For this reason, when you use a global approximation method, it doesn't work very well. So for example, if you use scikit-learn and you train a linear model on the output and input of the model, so those are the labels you will prevent, and those are the input, it won't work very well. However, there are other methods to do it. So for a local interpretation, what you could say is that, okay, I know that, for example, here, this data set here is a data set with blue and red points, and you can see that you have access to only a few data points there. So the cross, or let's say, has a label equals to 1, and the dots has a label equals to 0. This is just a classification, a binary classification problem. And the model that you trained, the black box that you trained, is represented here. So you have in red all the points that the model classified as red, and in blue everything that the model classified as blue. So as you can see, the model has pretty good result because it has 100% accuracy, but it's very hard to interpret. You don't know how to interpret it. So you would like to use a simpler model to approximate how the model is working. But as you can see, if you try to see to use a linear model, you won't be able to have something as complex as the model you have. So what you're going to do is to approximate. So you still are going to approximate the model with a linear classifier, but you will approximate it locally. So let's say you select this cross here, this red cross, and you want to understand how the model is working next to this red cross. So what you're going to do is to give to the model some data points. So those 1, 2, 3, 4 red cross, and those blue points here, those 1, 2, 3, 4 blue points, and you will try to fit the prediction of the model on those little points near the big red cross here. So how it works is that you won't look at all the inputs and all the outputs you have in your data set. You will look at one specific input. So we are in the local interpretability context. And for this input, you will look at all the input that are close to this one. And you will train a very simple model. So here, a linear regression model, a linear classifier model, to make the prediction just like your model did. If we want to be more precise, in reality, it's working a little bit differently than what I telling you. You won't just take into account those few points. You will take all of the points into account, but you will give more weight to the points that are closer to the red cross, to the sample you want to predict. So for example, this red cross here has almost no influence into the prediction of this model, but those points here will have some. And you can see that the bigger the symbols, so the bigger the crosses or the bigger the points, the bigger the importance in the prediction of the model. So this is called LIME model. So you have a library here that you can have a look on. You have the GitHub. This is where I found the image here I showed you. And on this GitHub page, they will give you some example of use of the LIME algorithm. Okay. So LIME is for local interpretable model agnostic explanations. Okay, so these were approximations methods, but there are other methods to try to understand model that won't use a simulation of the model. So this is like kind of a simulation of the model, and we can see that locally, so close to this red cross, it's not very far away from the real classification. So the real classification here is the border here. We can see between the red and the blue, and the approximation is the line there. So it's not exactly the same, but it's close. But for this border, it's not close at all. Like there is no relation between this and this, for example. So it doesn't work on the whole data set. Again, it only works locally. So the second group of interpretability methods that we will talk about today are sensitivity analysis. So sensitivity analysis is a big category. There are lots of different models that talks about it. I will talk mainly about two of them. The first one is called swap importance. It's from scikit-learn. You can also see here library if you want to. You will find it just by typing swap importance. And the way it works is that we say, okay, let's say we have those features. So price, bedrooms, longitude, latitude, bathrooms. It's like the feature for an apartment, and we would like to predict whether this, let's say, the number of square meters inside this apartment. We would like to predict the importance of each single feature inside this model. The principle we will use is that if a feature is not important, so for example, let's say the number of bathrooms doesn't have any importance in the prediction of the model, we will see that if we take, instead of the real value of the bathrooms, number of bathrooms, we take a random values, we will not see any change in the prediction of the model. So here we have a bunch of inputs, and we will select one, let's say the number of bathrooms, and we'll say, okay, for the number of bathrooms, I will take a random value instead of having the correct values. I will take a random values, and I will look at what's the influence on the output. If it has a big influence, then we will see that this value is important. If it doesn't have any influence, then this feature is not important at all. So here is a representation of what we could expect. So for example, for the price, we will see that it has a big influence because the price is highly correlated to the number of square meters. Same thing for number of bedrooms. Something for not a lot for longitude and latitude, and almost nothing for bathrooms. So these work pretty well, but we will face some kind of problem, the same problem we had before with the approximations, the global approximation, is that, let's say I take a random number of bathrooms and I take like 10 bathrooms. I say, okay, I would like to see what's going on if I take 10 bathrooms randomly. The problem is that the model is not made to make prediction on apartments with 10 bathrooms. So the influence that will have this random function on the output is not predictable. It maybe it will have a high influence, maybe it will have a very low influence, but it's not something that we would like to know about. This is not relevant. Um, and so the second problem we will face is the problem of the correlation between the features. Let's say you have a feature that is the price and another feature that is I don't know um, so you have the, the the price of the apartment that you will pay, and the price that the people that are selling the apartment will receive. There is a there is small difference between those two values, but we can easily see that those two values are highly correlated, because if you pay a lot of money, then the seller will receive a lot of money, and reciprocal, and this is true in both ways. If you select one feature that you take randomly, you won't be able to say, okay, I will take a random, very small value for the price that I receive, and a very high for the price you receive. This won't make any sense, and the prediction of the model, of course, won't be relevant either. So these are the problem with scikit-learn swap importance. And the way the next feature, the next um, library is working is trying to solve this issue by not taking just random values, but by calculating the derivative of the value. So instead of saying, okay, I take a random price, it will say, okay, I will just lower a little bit the price or increase a little bit the price and see what's the influence on the output. So it will calculate the partial derivative of the price according to the no, partial derivative, sorry, of the prediction according to the price. And this is better because you won't have such big nonsense coming on your inputs. Okay. I'll try to see there are questions. Can you please give a specific example how interpret a model not with A and B, but in realistic case? Um, I will give a specific example of how interpret a model in the second part of this presentation. If you have a specific example in your head, maybe you can try to give it to me, and I will try to give you some answers. Interpretability models are very easy to use. The main difficulties is how you understand how it works. So the realistic problem we'll try to solve in the next part of the masterclass is how to interpret a spam detector how to understand the interpretability models of the spam detectors. I hope this will answer your question. Okay. Finally, the next category of feature of interpretability is the one based on the Shapley values. So Shapley is a famous mathematician of the 20th century, and he developed a way to calculate how much money company should give to the people inside that company. So it's based on game theory mathematics, and it uses some axioms that are based on meritocracy. And so I won't have time to give you a lot of information about this Shapley algorithm. But the thing is that the Shapley values have very good properties. So, for example, the Shapley values guarantees that if you have two people that are working exactly in the same way in a company, they will receive the same amount of money, for example. Um, so even if it's not a good idea to use Shapley values in a real company in a real life, because those the, they are not aware of a lot of different factors. We can use it in a lot of other domains, and especially in interpretability. So you will maybe ask me, but what the relation between Shapley values and companies with the machine learning? In fact, if we try to think about it, we could say that the the company is just a bunch of people, and they are working together to make uh, some revenue. And for machine learnings or deep learning, it's just like a bunch of features that are working together or having some relation together in order to make a prediction. And if we take this kind of link between companies, Shapley values, and machine learning, we can use the definition of a Shapley values and apply it to our algorithms. So to be clear, Shapley values is just an equation that is giving you how much you need to give give how much money you need to give to someone, how much you evaluate the contribution of someone in a company. And we will use an approximation of this because it's too time consuming to be able to use it in AI. So you won't use Shapley values, properly speaking. You will use some approximation of it called Shap value. And those Shap value will give you some feedback about, okay, so this specific feature contributed a lot to the prediction of the model, and this other feature didn't contribute a lot in the prediction of the model. There are a few libraries that can give you an intuition of how Shap and Shapley values are working, and I will try to explain it to you in this specific example. So, for example, here we are going to use a data set that is called MNIST, and it's just written figures. So, for example, this is a written figures, and we trained an algorithm to try to predict what's the figure that is presented here. So it's a classification algorithm, and we would like to say whether it's a 0, a 1, a 2, etc. And here we calculated the SHAP values of every single pixel. So pixels here are just like features in tabular in tabular data sets. And we would like to say what is the contribution of every single pixel in the final prediction. And for the prediction of the 2, for example, for the prediction of 0, we can see that there is no pixel that contributed to the final decision because everything is in white or in gray. So the SHAP values of those pixels for the prediction of the 0 is 0. So if you don't really understand, these are the pixels for the prediction of the 0, pixels for prediction of the 1, pixels for prediction of the 2, 3, 4, 5, 6, 7, etc., etc., etc. And here, for example, for the prediction of the 2, we can see that the pixels on the top of the 2 and the pixel on the bottom of the 2 had a very high SHAP values. So those pixels had a very high contribution to the model. So this is just like if you were saying, okay, here we can see that the model looked specifically at those um, um, pixels here in order to make his prediction. And of course, this prediction was 2. This number is 2. This figure is a 2. We can see the same thing for the 1, nothing for 0, nothing for 2, nothing for 5, etc. But here, for example, for number 4, we can see that there are some blue pixels here. Blue pixels is like pixels that have a negative SHAP values. So this means that the model so that this figure here looks a little bit like a 4, but he was expecting to see some black pixels here. He was expecting to see some information there to be able to say that this is a 4. And because it didn't see them, it had a negative contribution to the prediction. So it's like I didn't predict 4 because I saw that there were no pixels, no black pixels here. And same thing for the 9. We can see that I didn't predict 9 because there are no black pixels here. So it's only one stick and there is no curve here. It's even clearer with the 4. So for example, if you imagine that those two sticks are linked with each other, it would be a 9. But because it's not, it's only a 4 here. And so the model saw that there were no any black pixels here, so it has a negative effect, negative contribution to the prediction of the model. But because there were no black pixels here, the fact that there were white pixels on the top had a positive effect on the fact that the prediction was a 4. So you can see that even if there are white pixels, the model looked at it closely to make sure that this was a 4 and not a 9. Okay, so this is how Shapley values works. It can be used on textual information. It can be used on images. It can be also used on tabular expression. There are a lot of ways to use SHAP. If you are interested in understanding how SHAP works, I strongly encourage you to look at this website here. I will give you the link in the description of the YouTube video to see how to use it and how it works. Okay. Before we start the use case, I'll try to see if there are any questions. Okay. Not any question for now. Let's go. So the use case will be about what to recommend in terms of data preparation to improve interpretability. This is a good question. Of course, it depends a lot on the data you have initially. If your data set is images or textual information, it will not be the same, of course. But to interpret the model, things you need to be sure is that your data is quality, has a lot of not um, bad quality data, because if you have bad quality data, then your model will work like not randomly, but it will take arbitrary decisions, and the interpretability model will use those arbitrary decision to understand how the model is working, which is not something you would like to have. So you have to make sure the data has high quality and is big enough, if you can, of course, so that you can see all the space where the model is making prediction. Because if too narrow, then you will interpret only part of the model. You will understand the model partially. So you will have to make sure that it's diversified enough. I know that this is a very generic answer. I will try to maybe give you some hints in the 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 use case I will share with you. So here, I would like to uh, use a model that is able to detect spams. So we have some emails that are coming in, and my model will be able to say that some of the emails, so the blue ones, are not spams, and some others, the yellow ones, are spams. And afterwards, we will use some interpretability method to try to understand what's going on inside this model. Uh, Oops, here, yeah. Um, okay, so I found a data set on the internet that was containing around 5,000 emails that were labeled by humans, so labeled by hand. Zero are the one that are not spam, and one are the one that are spam. They were collected in 2001, so they are a little bit old, and from an American company that we will speak a little bit about afterwards. And so let's look at it closely. We will take an example here of a mail that is not a spam. So we have some information about something coming on the next month, and yeah, on Thursday. Okay, so because it's coming from a company, it's mostly professional emails that are written in with a rich language, but there are some exceptions inside. And so the label for this specific mail is zero because it's labeled as not spam. Now let's see what's happening in spam labeled text. We have some information about, so it's a team of government officials coming from a committee, and they will require your assistance in a matter that involve investments of monies. Okay, and so they would like you to transfer money to their account, and most importantly, they would like to do it yeah, immediately. Like a lot of times in spams, they want you to give us money and immediately, otherwise it will be too late. So it's I didn't show you the whole spam because it was very long, but it's very uh, uh, like um, obviously a spam here, and so the label is one. Okay, so we will apply the usual preprocessing step here. So nothing very special. We just split the data set in two. First half will be used for training. Second half will be used for testing. If you are not aware of how this works, it's just like we have the whole data set that will cut in half to make sure that we will be able to test the model on something he never saw. And now we will classically use the convectorizer method to have access to vectors instead of text. This is usually something you would like to do at first to see if you can reach the goal that you want to reach in order to make your classification or the task you want to solve. So convectorizer is just telling me that, for example, here in the first row of my data set, so for my first email, the word please appeared once, the word tomorrow appeared once, the word money appeared 0 times, and the word immediately appeared 0 times. And for the second row of my data set, which is a spam here, the word please and tomorrow appeared 0 times, but the word money appeared 3 times and immediately once. So the convectorizer coming from the library of scikit-learn is very easy to use. You just have to fit it on the train set, and then you can transform both the train and the test set. So now I have a data set that is not containing any more words and text, but the number of occurrences of each word in each email. And we will as soon as it comes, we will use a naive Bayes model. So from scikit-learn, it's called multinomial NB. And this naive Bayes model will be able to make the classification between spams and not spams. And when we feed it on the trained data set and test it on the test data set, we see that we have an accuracy of 98%. And on the confusion matrix, we see that the results are very good. So, for example, here around all the true mails, so not the spams, we were able to classify it correctly 734 out of the 729 emails. So it's very, very good. And for the spams, it's very good also. We were able to classify correctly 285 emails out of the 296 spams. So conclusion, we are very happy because our model is very, very good to make classification. And as soon as I see those scores, I had to be a little bit suspicious because this model here is very simple in reality, and it's hard to believe that with only one small prediction, I'm able to reach that level or performance of accuracy. So before I go further, we'll try to understand how our model works. So we'll try to look if it's working when I create my own email. So here I created some random emails like click here to make $1,000 in 1 day. And the prediction is still correct. I see one here. And hi, can we meet this afternoon? Also, this is probably not a spam. And the prediction of my model is that it's not a spam. So, okay, I tried to understand why my model can be biased or how my model was working. But when I test it, it seems like it was working very well. And I wasn't able to find any email that was giving me. Oh, sorry, that was from the beginning. I was on the wrong presentation. Sorry. Okay. Well, we got a bit before. You can see what I did. So this is my data set. I have the text here, the label there. I have access to some data there. So you can try to look at it a little bit closer. So it's classical mails. So these are for some scheduled times. Yeah. And here, this is the spam. So the team of government officials that request you immediately to contact to be favorably disposed, and they would like to yeah, to transfer to your account money. So this is obviously a spam. So here we just split the data set in two, and then we'll use the convectorizer, which is going to give me some data set looking just like that. So for example, for each row, I will have the number of occurrences of each word in my vocabulary. So here, please, tomorrow, money. So for example, for this row, I know that the word please is here once, the word tomorrow once, the word money 0 times. And for the spams, it's pretty much working the same way. And here I train my naive Bayes model there. So I created the multinomial naive Bayes model here. I fitted it on the X train with the label of Y train, and then I looked at the results on the testing set. So what I see is that using this very simple data set here, so I only know which word appear in which email, and I was able to see uh, uh, to have a very high accuracy, so 98% of accuracy. And if I look at the confusion matrix, it's very good. So only 16 bad predictions over the whole data set, over the whole testing data set. And here I was just trying to make some prediction on my own emails. So it's something that I wrote myself, like click here to make $1,000 in one day, or can we meet this afternoon? So this is obviously a spam, and this is classified as a spam. And can we meet this afternoon is obviously not a spam, and is classified as not a spam. So before we continue, I will check if there are any questions. I'm sorry for this problematic. Okay. The question now is to understand how we will be able to understand what's going on in that model. We are of course a little bit suspicious, because we see that this seems weird. It's too easy. It shouldn't be as easy as it is. So we will have to use some interpretability methods to make sure there is no trick here used by our model. So naive Bayes is a pretty simple model. In fact, we'll try to explain how it works quickly, and then we'll try to interpret it. Concretely, when we have those kind of information, we can see that generally speaking, over the 1,000 spam that I have in my data set, the word please appears 60 times. And in my 2,000 not spams email in my data set, I have 600 emails with the word please. So when I see the word please, I have a strong opinion of the fact that it will probably be something that is not a spam, because here it's more likely to be something that is not a spam. It is the same principle with tomorrow, where there are a lot more tomorrow words in the not spam category than in the spams category. So how the naive Bayes model will work, he will try to estimate the probability of an email to contain the word please, knowing that it is a spam, and the probability of a word to contain the word please, knowing that it is not a spam. So those two probabilities can be calculated that way. So you just take the number of times the word please appear in the not spams category over the total of emails, and same thing for the spams. So it's here it's 600 out of 2000, so it's uh, 0.3, so 30% of the times. And for the spam, it's 6% of the times only. And so those two probabilities would be used in order to see whether this email is a spam or this email is not a spam. So how it's going to work, if we have an email, let's say with only two words like please tomorrow, this email, the probability of this email to of being not a spam, so probability of being not a spam knowing that it contains those two words please tomorrow, is proportional to the probability of containing please, knowing that it's not a spam, times the probability of containing tomorrow, knowing that it's not a spam, times the probability of being not a spam. And which will do the same for the spam category. I know that is probably a little bit hard to understand when I explain it just with my hands, but concretely, it's based on two things. Those figures here, it's the fact that there are more please in the not spam and the spams, and the total number of spams here. And it's by default, it will consider that all the words are completely independent. That we won't use the dependence between two words in one sentence. We'll say that they are just appearing randomly in the emails, even if it's not really the case. So it's a big approximation here, but it's still working pretty well. And so now the question is, how can I say whether the final classification? How can I say whether the mail is a spam or is not a spam? I can just compare those two probabilities, and I will say that the email belongs to the most probable category. So, for example, for please, I can see that if the email is only containing the word please, it's 5 times more likely to be not a spam than being a spam. And for the word money, it's 3 times more more likely to be a spam than not a spam. And what you can see also is that those words here that we're looking at are also the features of my data set. Those are the features of my initial data set. So I can use those features to say what is the importance of the importance that a model is giving to one specific feature. So for example, the feature please is very important because it's very easy to discriminate whether the email is a spam or not a spam using the word please. But let's say we have the word the here, which is a word very common that we will see in every email. The ratio here will be close to 1 because it's not giving you any information about the fact that the email is a spam or not a spam. So this feature won't be very interesting. As a contrary, the word please and money are very interesting because they are giving you a lot of information. So what you're going to do is to estimate the importance of the features based on those ratios. So to be more specific, we won't just look at those ratios, but we'll use the maximum of the ratio and the inverse of the ratio to make sure that even if the feature is close to 0, it's still very interesting. And so we will look not at 0.3, but 1 over 0.3, which is around 3. Okay, and so we'll be able to look at it directly on our data set. So if we look at it directly in our data set, we can yeah, so I didn't show you how to get to this feature important. There is a few steps to go that I won't be able to explain to you, but there are some calculations, some operations to make. First of all, you take the maximum in the between the ratio or the inverse of the ratio. Then you take the logarithm of it to have something that is more coherent, and then you just here I just printed the 10 features with the maximum importance. And here, concretely, I see that those features have some names that I don't really understand here, like who, Enron, ECT, meter, HPL, Darren, etc., etc. And so there, it seems like there is something wrong going with the importances of my features based on those importances here. Okay, I will make sure there is no question here. Yeah, I voluntarily didn't make distinction between the number of appearances and the fact that the email is having the world. There is a small approximation. We are looking at the number of appearances. So it's when you see is 600 times the word please, it means that when you make the sum of the total number of times the word please appear in the not spams, it's reached 600. Yeah. Okay. So now that we are able to use an interpretability method, first of all, let's try to see what kind of interpretability method you used. Because it's chuk- chuk, we used specific interpretability because we were able to, because naive Bayes is very simple, we were able to look directly inside this algorithm. We were able to look inside the algorithm without using any agnostic method. And also what I'm showing here is the importance of the features generally speaking. So it's global interpretability. However, if I would like to, I would be able to see the importance of the features in one specific email, because I would be able to see if the word is appearing or not in the email, and see what's the consequence of the prediction. Okay. So we stopped here. So I can see that there are some strange words here, but I would like to say whether those words are informative for the model to say if it's a spam or not spam. So as I told you before, I said that for when it's bigger than 1, this ratio, it will tell you that this is probably not a spam. And when it's lower than 1, it will tell you that it's probably a spam. So we will split these importances in two to see whether it's giving you the information of this is a spam or this is not a spam. And when we do it, we have those features. So for the spam, we have NBSP. I don't really know what this means. TD 2004 Computron pills. So pills, it's like something they want to sell you. And for the non-spam, we have Who, Enron, ECT, Mater, HPL. So at this moment, it seems like my model is biased because it gives a lot of importance to words that don't ring me any bells. So if I try to search on the internet, for example, for Enron, what I will see, yeah, it's in French. Sorry. Yeah, that Enron is a company based in Houston that was founded by etc. etc. And in the end of 2001, reported financial condition was sustained by, and so the company went bankrupt because of fraud and corruption. And so if I look at it closely, I will see that the company was uh, the, 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 the legislation had to look at the emails of the company to say to understand what was about this fraud and corruption scandal. So in the end, I understand that the emails I was able to find are coming from this company here, N1, and the reason why I see that those words here like who and run on ECT are so important is because it's very specific language for this company that is an energy company that use a lot of gas. So for example, if I try to look at the data, I can see those words appear. HPL, Who for Houston, Enron because it's the name of the company, ECT because it's probably some kind of address that they use in the company, Meter, it is something that they use to say that they are going to make some work on one specific place of the pipeline they use to bring gas, etc., etc. And those words are very very easy for are making the model very very easy to understand whether it's a spam or not. So for example, if I take my example that I used before again, like click here to make $1,000 in one day. If I just add the name of the company and run, then the prediction is coming from not a spam, a spam to not a spam. And if I talk about some pills, for example, then the prediction will give me that it's a spam because pills are categorized as spams here. So the conclusion I can make here is that even if my model is working very well on the email I used here, 98% accuracy is very, very good. I won't be able to use it in a more generic way. Like I won't be able to commercialize this model because it's biased a lot. So for example, if I'm a writer of spams and I know that when I write and run, this is not categorized as spam, this is not detected, then I will write and run in every single of my email and it will work very easily. So in the end, you can see that even if it's working very well, there is probably still a lot of work to do to make sure that I will be able to get over those biases here. Uh, to maybe try to use more emails coming from other places and to anonymize maybe some of it to take off every single appearance of the word Enron or who. So it's probably going to be harder than what I thought at the beginning. Okay. So, what can I do in order to correct those bias? First of all, the main way to do it is to make some modification in the data set. So maybe try to anonymize it or try to find more data. But finding more data usually is very expensive because it needs to be localized, which can be very long, or I can modify the functioning of the algorithm. So for example, if I just get out in my data set here, if I take over the feature, the column related to the Enron part or the Houston part, everything that has a link to the company I was trying to understand, uh, I will get rid of some biases that I have in my data set. Because it needs some human intervention, it's usually very long and very complex. So even if interpretability is useful, it won't give you the solution of the problem you will face. So when you have a bias, the interpretability model will tell you, okay, this is the bias you have, but you won't have access to the way to solve this bias. Okay. I think this is it for my presentation. I will stay a little bit to answer the question. I hope you liked what you were able to see today. There were the question of Anna about the specific example. I hope that the example I gave you at the end answered your question. Otherwise, I'm still here for a few minutes to answer them. Thank you for your attention. Uh, what in this case using the external emails? What do you mean by external emails? Yeah. So of course, if we can have access to some other emails, it will be better. The only thing is that we need to have a database of email that are that only have the labels. Otherwise, it will cost a lot. So we have to find somewhere a data set, or we have to do it ourselves. A data set with emails with the label spams or not spam. Oh, okay. You mean well, okay, an internal email within the company. Yeah, probably. I don't know if the information can be found directly in the data set I found, but yeah, maybe based on the mail email address of the sender, we could be able to say whether it's a spam or not, or to simplify a lot the work of the people that will say whether it's a spam or not. Okay. Um, if there is not any more question, we will end the session now. Thank you again for your attention. This session will be available on YouTube. And so if you are already watching on YouTube, don't forget to like and subscribe if you like the video, and to maybe watch other videos that we're making very regularly on this YouTube channel. Have a good day. Goodbye.